Welcome to the deep dive. Today, we're going to be looking at some excerpts from a 10th grade science textbook
Okay.
and diving into the world of carbon and its compounds.
Right.
It's pretty fascinating to think about how one element, can be the building block of so much.
Yeah.
From the air we breathe to the diamonds on our fingers,
Right.
ready to unlock the secrets of carbon.
Absolutely. It's really quite remarkable how carbon, despite being relatively scarce, in the Earth's crust and atmosphere,
Yeah.
manages to be the backbone of life as we know it.
That's what I find so intriguing. It's like discovering that the most elaborate structures are built with the rarest materials.
Yeah.
So how does carbon achieve this incredible feat?
Wow.
The textbook mentions covalent bonding as a key factor.
Uh-huh.
Could you break that down for us?
Certainly. In simple terms, covalent bonding is all about sharing electrons.
Okay.
Unlike ionic bonds, where electrons are transferred from one atom to another,
Uh-huh.
covalent bonds involve atoms sharing electrons to achieve a stable configuration.
So it's like atoms teaming up to complete their electron collections.
Exactly. Let's take a simple example.
Okay.
A hydrogen molecule, H2.
Okay.
Each hydrogen atom has only one electron, but they need two to achieve a stable state.
Right.
So they share their single electrons, forming a covalent bond that holds them together.
Ah, so sharing is caring in the atomic world too.
Yes.
And this sharing can happen with more than one electron, right?
Yes.
The textbook mentioned double and triple bonds.
You're absolutely right.
Okay.
Take oxygen, for example.
Okay.
Each oxygen atom needs two more electrons to complete its outer shell.
Uh-huh.
So they form a double bond by sharing two pairs of electrons.
Okay.
Nitrogen takes it even further, forming a triple bond by sharing three pairs of electrons.
Wow.
It's this ability to form multiple bonds that contributes to carbon's incredible versatility.
Okay. So this brings us to another point that caught my attention.
Okay.
Carbon's tetravalency.
Right.
What exactly does that mean and why is it so significant?
Tetravalency simply means that carbon has four electrons available for bonding.
Okay.
Think of it as having four arms, each capable of reaching out and forming a bond with another atom.
Okay.
This allows carbon to create complex and diverse molecular structures.
I see. So carbon's like a master connector,
Yes,
linking up with other atoms in countless ways.
exactly.
This reminds me of the textbook's example of methane CH4.
Methane is a great example of carbon's tetravalency in action.
Okay.
Each carbon atom forms four single bonds with four hydrogen atoms,
Okay.
resulting in the simple yet significant methane molecule.
And methane plays a crucial role in our lives, doesn't it?
It does.
It's a major component of natural gas, which is used as fuel for heating and cooking in many homes.
That's right. However, methane is also a potent greenhouse gas,
Oh.
which brings up important considerations about its environmental impact.
Yeah.
It's a reminder that even simple molecules can have complex implications for our planet.
It definitely highlights the importance of understanding both the benefits and challenges associated with different carbon compounds.
Absolutely.
Speaking of variety, the textbook section on allotropes blew my mind.
Oh, yeah.
Diamonds and graphite, both made of pure carbon, yet so different in their properties.
Right.
How is that even possible?
It all comes down to the arrangement of carbon atoms.
Okay.
In diamonds, each carbon atom forms strong bonds with four neighboring carbon atoms in a rigid three-dimensional lattice structure.
Okay.
This gives diamonds their exceptional hardness.
Right.
Graphite, on the other hand, has carbon atoms arranged in layers
Uh-huh.
with weaker bonds between the layers.
Okay.
This allows the layers to slide past each other easily, making graphite soft and slippery.
That's incredible. The same element can have such vastly different properties,
I know, it's amazing.
depending on how its atoms are arranged.
Yeah.
And the fact that we can actually synthesize diamonds by subjecting pure carbon to extremely high pressure and temperature
Right.
just adds to the wonder.
It's a testament to our growing understanding of how to manipulate matter at the atomic level.
Yeah.
And while diamonds and graphite might be the most well-known allotropes,
Uh-huh.
there's another fascinating one, fullerenes.
Ah, yes, fullerenes. The textbook mentioned Buckminster fullerene C60 with its unique soccer ball-like structure.
Yeah.
It sounds like something straight out of science fiction.
It's a fascinating example of how carbon can form complex, symmetrical structures with intriguing properties.
Right.
Fullerenes have potential applications in nanotechnology, electronics, and even medicine.
It seems like carbon's ability to create different structures is key to its versatility.
Yeah.
The textbook mentioned catenation carbon's ability to bond with itself to form chains as being crucial for creating the vast array of organic compounds found in nature.
Precisely. Catenation allows carbon atoms to link together, forming long chains that can be straight-branched or even form rings.
Wow.
This ability, combined with its tetravalency, opens up a world of possibilities
Okay.
for creating complex molecules with diverse properties.
So carbon's like a master Lego builder,
Yes.
creating intricate structures with endless combinations.
Exactly.
And the textbook mentioned hydrocarbons.
Yes.
Are those essentially these carbon chains with hydrogen atoms attached?
Yes. Hydrocarbons are the simplest organic compounds consisting only of carbon and hydrogen.
Okay.
They can be further categorized as saturated or unsaturated. Saturated hydrocarbons like ethene C2H6
Okay.
have only single bonds between carbon atoms, while unsaturated hydrocarbons like ethene C2H4 contain at least one double or triple bond.
So it seems like even with just carbon and hydrogen, there's already a lot of variety.
There is.
And then to make things even more interesting, the textbook introduced the concept of structural isomers.
Right.
It's amazing how molecules with the same chemical formula, like butane C4H10, can have different structures and consequently different properties.
Structural isomers are a testament to carbon's amazing versatility.
Yeah.
It's like having two buildings built with the same materials, but with different blueprints.
Yeah.
They might look and behave differently, even though they're made of the same stuff.
It's like carbon is constantly surprising us with its ability to create diversity.
Right.
And we can't forget about cyclic hydrocarbons, where carbon atoms form rings, like in benzene C6H6,
Right.
which is a key component in many industrial processes.
Exactly. Benzene is a fundamental building block for countless organic compounds, showcasing yet another facet of carbon's incredible versatility.
It's mind-boggling how carbon's unique bonding properties lead to such a vast array of compounds.
It is.
But wait, the textbook mentions something called functional groups.
Yes.
What role do they play in all of this?
Functional groups are like accessories for carbon chains.
Okay.
They're specific atoms or groups of atoms that attach to the carbon backbone and impart distinct properties to the molecule. Think of them as adding unique functionalities to our carbon Lego creations.
So they're like adding special features that change how the molecule interacts with the world.
Exactly. For example, an alcohol group makes a molecule more soluble in water and can give it a characteristic scent. Aldehydes and ketones contribute to the flavors and aromas of many fruits and spices.
Okay.
And carboxylic acids, like acetic acid and vinegar, give that characteristic sour taste.
It's amazing how these functional groups are responsible for the incredible diversity of smells, tastes, and properties we encounter in our everyday lives.
Absolutely. They're the key to understanding how carbon compounds contribute to the complexity and beauty of the natural world.
This deep dive is already proving to be an eye-opening journey into the world of carbon. From covalent bonds to allotropes and functional groups, it's clear that carbon is a true master of chemistry.
It is.
And we've only just begun to explore its fascinating world.
That's right.
There's much more to uncover, including the properties and uses of specific carbon compounds like ethanol and ethanoic acid, which we'll delve into in the next part of our deep dive.
Okay.
I can't wait to learn more.
Me too.
It's amazing how these simple molecules play such diverse roles in our lives.
Yeah.
Until next time, keep those minds curious.
Great.
Welcome back to our deep dive into the world of carbon and its compounds. In the previous segment, we explored how carbon's unique bonding properties allow it to create this incredible array of molecules.
Right.
Now let's shift our focus to two specific carbon compounds that play a significant role in our daily lives:
Okay.
ethanol and ethanoic acid.
Right.
What's fascinating is how these relatively simple molecules have such diverse applications.
It's truly remarkable. Let's start with ethanol, often simply referred to as alcohol.
Okay.
It's a clear, colorless liquid that mixes readily with water, making it a versatile solvent used in a wide range of products.
That's why that bottle of iodine in my first aid kit has that distinct alcoholic smell.
Yeah.
I never realized ethanol was the culprit.
Exactly. Ethanol helps dissolve and carry the iodine, making it easier to apply.
Right.
Of course, ethanol is most commonly known for its presence in alcoholic beverages.
Yeah.
But it's important to remember that while it's widely consumed, ethanol can be toxic in large quantities.
It's a good reminder that even familiar substances can have a darker side.
Right.
The textbook mentioned that even small amounts of pure ethanol, also known as absolute alcohol, can be lethal.
Yes.
It really underscores the importance of responsible consumption.
Absolutely. And speaking of ethanol's chemical reactions, you might recall from the textbook that it reacts with sodium in a rather dramatic fashion.
Oh, yes. Dropping a tiny piece of sodium into ethanol is like creating a miniature volcano in a test tube.
Exactly.
It fizzes and bubbles, releasing hydrogen gas. I remember being captivated by that demonstration.
It's a striking visual representation of a chemical reaction in action.
Yeah.
The sodium reacts with the ethanol producing hydrogen gas and sodium ethoxide.
Okay.
It's similar to how other alkali metals react with water,
Right.
highlighting a pattern in chemical behavior.
It's those patterns that help us make sense of the seemingly complex world of chemistry.
Yes.
The textbook also mentioned ethanol's role in producing ethene, an unsaturated hydrocarbon.
Right, that process is called dehydration. By heating ethanol with concentrated sulfuric acid, a strong dehydrating agent, we can essentially remove a water molecule H2O from ethanol, leaving us with ethene.
So it's like squeezing the water out of the ethanol molecule to create something new.
That's a good analogy.
Yeah.
It highlights how we can manipulate chemical reactions to transform one compound into another.
This reminds me of the textbook's discussion about the effects of alcohol on living beings. It mentioned how excessive alcohol consumption can impair brain function and lead to a range of health problems.
It's a sobering reminder of the potential consequences of misusing even common substances.
Right.
Ethanol, when consumed, is metabolized in the liver.
Okay.
But in large amounts, it can overwhelm the liver's capacity to process it, leading to a buildup of harmful byproducts and potentially damaging the liver cells.
It's a complex issue with both social and biological implications.
Absolutely.
And the textbook even touched upon methanol, a close relative of ethanol,
Right.
but far more dangerous if ingested.
Methanol is indeed a serious concern. Unlike ethanol, which is metabolized into relatively harmless compounds, methanol is converted into formaldehyde in the liver.
Okay.
Formaldehyde is highly toxic and can cause severe damage, including blindness.
It's a stark reminder that even subtle differences in molecular structure can have drastic consequences.
It can.
It makes me think about denatured alcohol, which the textbook mentioned is often used in industrial settings.
Denatured alcohol is essentially ethanol that has been rendered undrinkable
Okay.
by adding toxic substances like methanol or other denaturants.
Right.
It's a safety measure to prevent accidental ingestion, especially since ethanol is used in so many household and industrial products.
So it's like putting a warning sign on the ethanol to say, don't even think about drinking this.
Exactly.
It's fascinating how chemistry is used to address real-world safety concerns. Now let's switch gears and talk about ethanoic acid, also known as acetic acid.
Okay.
Most people probably associate it with vinegar, right?
Absolutely. Vinegar is essentially a diluted solution of ethanoic acid in water, typically around 5–8%.
Right.
It's that characteristic sour taste and pungent smell of vinegar that we can attribute to ethanoic acid.
I've always wondered about that. It's amazing how such a simple molecule can create such a distinctive flavor profile.
It is.
The textbook also mentioned ethanoic acid's role as a preservative.
That's right. Ethanoic acid's acidic nature creates an environment that's hostile to many microorganisms, making it an effective preservative for pickles, relishes, and other food products.
Right.
It's a natural way to extend shelf life and prevent spoilage.
It's like ethanoic acid is acting as a microscopic guardian, protecting our food from unwanted invaders.
Yeah.
And speaking of its acidic nature, the textbook classified ethanoic acid as a carboxylic acid.
Right.
Which means it's a weak acid compared to something like hydrochloric acid.
Exactly. While ethanoic acid does release hydrogen ions H+ in solution, which is characteristic of acids, it doesn't ionize completely like strong acids.
Okay.
This means that its effect is less intense.
So it's acidic, but in a more mellow way. It's like the difference between a gentle drizzle and a torrential downpour.
That's a great analogy.
Yeah.
It helps to visualize the concept of acid strength.
The textbook mentioned esterification as one of ethanoic acid's key reactions.
Yes.
Can you explain what that entails?
Esterification is a reaction between a carboxylic acid, like ethanoic acid, and an alcohol.
Okay.
In the presence of an acid catalyst, they combine to form an ester and water.
And esters are those fascinating compounds that give us the delightful fragrances of fruits and flowers.
Precisely. Esters are responsible for a wide range of pleasant aromas, making them essential ingredients in perfumes, flavorings, and even cosmetics.
It's like chemistry is behind the scenes creating these invisible symphonies of scent that enrich our sensory experiences.
It is.
And the textbook mentions saponification, which is related to soap making.
Right.
Is that also a reaction involving ethanoic acid?
Saponification doesn't directly involve ethanoic acid, but it does involve another type of carboxylic acid, long-chain fatty acid.
Okay.
In saponification, these fatty acids react with a strong base, like sodium hydroxide, to produce soap.
So soap is essentially a salt of a fatty acid.
Yes.
It's incredible how a simple chemical reaction can produce something we use every day to keep ourselves and our surroundings clean.
It is.
The textbook also mentioned that ethanoic acid, like other acids, reacts with bases to form a salt and water.
Right.
I remember that classic experiment with baking soda and vinegar,
Yeah.
which created a fizzing eruption of carbon dioxide gas.
That's a memorable demonstration of acid-base chemistry, when ethanoic acid reacts with sodium bicarbonate,
Uh-huh.
commonly known as baking soda.
Right.
It produces sodium acetate, a salt water, and carbon dioxide gas,
Okay.
which causes the characteristic fizzing.
We've covered a lot of ground exploring the properties and reactions of ethanol and ethanoic acid.
We have.
It's remarkable how these seemingly simple molecules play such diverse roles in our lives.
Yes.
From medicine and industry to food preservation and even cleaning products.
Right.
It's a testament to carbon's incredible versatility as a building block for creating a vast array of compounds with unique properties.
It is.
And in our final segment, we'll continue to explore carbon's remarkable capabilities by delving into the chemistry behind soaps and detergents.
Sounds good.
I'm eager to learn more about how these everyday products utilize the principles of chemistry to keep our world clean.
Okay.
Welcome back, deep divers. We've been on this incredible journey, through the world of carbon and its compounds, from that simple methane molecule to the complex structures of fullerenes and the fascinating properties of ethanol and ethanoic acid.
Right.
But what about something we use every day?
Yeah.
Maybe without even thinking about the chemistry involved.
Right.
Today, we're going to wrap up our deep dive by exploring how we keep things clean.
Okay.
The chemistry of soaps and detergents.
It's easy to take soap for granted, but its ability to dissolve greasy dirt in water, something that wouldn't normally happen,
Yeah.
is quite remarkable.
Yeah.
It's a perfect example of how understanding chemistry can help us solve everyday challenges.
I remember that experiment from the textbook where you add oil to water.
Yeah.
And they just don't mix.
Right.
But add a little soap,
Uh-huh.
and suddenly you get this cloudy mixture,
Yeah.
and the oil seems to disappear. What's the secret behind soap's cleaning power?
The key lies in the unique structure of soap molecules.
Okay.
They're a bit like double agents, with one end that loves water, hydrophilic,
Uh-huh.
and the other end that loves oil, hydrophobic.
Okay.
This dual nature allows them to act as a bridge between oil and water, which normally repel each other.
So it's like soap molecules are playing matchmaker between two substances that can't stand each other.
That's a great way to put it. When soap molecules encounter oily dirt,
Uh-huh.
they surround the oil droplets with their water-loving heads pointing outward,
Okay.
and their oil-loving tails pointing inward, trapping the oil inside tiny spheres called micelles.
So the oil gets locked up inside these micelles
Yes.
and can then be washed away with water.
Exactly.
It's like a microscopic cleaning crew.
Precisely. The micelles, with their oily cores and water-loving exteriors, can easily disperse in water, effectively carrying the dirt away.
Okay.
But there's a catch, as the textbook pointed out.
Yeah.
Hard water can throw a wrench in this cleaning process.
Ah, yes. Hard water, the bane of clean dishes and sparkling showers.
Right.
I've always wondered why soap seems to be less effective in hard water areas.
Hard water contains dissolved minerals, mainly calcium and magnesium ions, which react with soap molecules to form insoluble salts.
Right.
These salts precipitate out of the solution, forming the familiar scum that cleans the surfaces and makes cleaning a chore.
So that's why I feel like I need to use twice as much soap when I'm visiting family in a hard water area.
Right.
It's like the soap is battling those minerals instead of tackling the dirt.
Exactly. And that's where detergents come in.
Okay.
Detergents were developed as a solution to the hard water problem.
Right.
They have a different chemical structure than soaks,
Uh-huh.
often containing sulfonate groups instead of carboxylate groups,
Okay.
which are less likely to react with those pesky calcium and magnesium ions.
So detergents can handle the tough ions in hard water
Yes.
and still effectively clean away dirt and grease.
That's right.
That explains why they're used in laundry detergents and dishwashing liquids, which
Wow.
often have to contend with hard water.
Precisely. It's all about tailoring the chemistry to the specific cleaning challenge.
Right.
And just like soaps detergents, also form the cells trapping dirt and grime so it can be rinsed away.
It's fascinating how a little bit of chemistry can make such a big difference in how we keep ourselves and our homes clean.
It is.
Well, we've covered a lot of ground in this deep dive into the world of carbon and its compounds.
We have.
From the basic principles of covalent bonding and the unique structures of carbon allotropes,
Right.
to the properties and reactions of ethanol and ethanoic acid,
Yeah.
and the chemistry behind soaps and detergents, it's been an incredible journey.
It has.
And we've only scratched the surface.
That's right.
Carbon, with its remarkable ability to form diverse and complex structures, continues to amaze and inspire scientists.
It does.
Who knows what incredible materials or technologies we might create using carbon as a building block in the future.
Exactly.
It's an exciting thought. So, dear listeners, I encourage you to keep exploring the chemistry of everyday things.
Yeah.
You never know what fascinating discoveries await. Thanks for joining us on this deep dive. Until next time, keep those minds curious.